universe. Unless you fix some strange initial condition. Someone fixed a strange initial condition over here. That's another way of expressing the problem, by insisting that the constant potential dominate over the matter, the radiation, everything else. That's a very strange condition, given this simple scaling argument from the Friedmann equation. That's a way of expressing the strangeness of the initial condition of inflation. It's very unnatural. Yeah.
So what would be the initial condition for this model?
Well, if you go back in time, it would be a nearly empty universe. With just a minuscule, arbitrarily small smear of energy density of various sorts that for some reason began contracting infinitely in the past. Not so different than, say, than a full de Sitter universe, which begins infinitely big and is contracting. This isn't de Sitter, but I'm saying it's no different than any other cosmology which has no beginning. It has no beginning. It's a complete cosmology.
But isn't that still somewhat unsatisfying? Like you said, for some reason it did this.
Well, that depends on whether it's robust. That is to say, if I put lots of stuff, different stuff here, and extrapolate back, and it brings me to the same beginning, then that's a good situation. That's what we were hoping was going to happen in inflation, that when we extrapolate back, that most trajectories would come back and give me 60 e-folds, would give me the condition I wanted. Here, no matter what junk I put in the, almost not matter what junk, but for a wide range of junk I put in the middle, I go back, it's going to eventually be just spread out. So in fact, it's the opposite of the case of inflation. I'm actually led back to an initial condition, which is pretty much independent, very insensitive to the junk I put in there. It's going to look like it's mostly thinned out, nearly arbitrarily big universe. So think of it, that's the story. That's all I can say about it. That's what occurs if you have just a single bounce case. Okay? Other questions? Okay, so that's important. Before we're doing anything at all, we've already solved two problems. Now, on this side of the story, the idea is not to change the Big Bang story, so we assume that there's going to be just matter and radiation in the universe, which means that your epsilon is either going to be equal to 3/2 for matter or equal to 2 for radiation. On this side of the story, well, we don't know what happens when the universe is contracting. We don't know what created all this matter and radiation. But let's borrow an idea that was already supposed to be there in inflation, which is that there's some scalar field which is driving this contraction. So it won't be the scalar field with this potential. We'll talk about possible potentials it could have. But it has the common feature that at the end of the story, the field is somehow rolling around a minimum, and it's rolling around that minimum. It's rapidly oscillating. A rapidly oscillating field will tend to radiate, just like a rapidly oscillating charge, and it will tend to convert its energy into matter and radiation. We'll borrow that same idea. We'll assume this field is dominant here. It has some epsilon, and then somewhere around the bounce, or after the bounce, it converts to matter and radiation, and that's how we get the matter and radiation we see today. So you might think that's a little bit arbitrary, a little bit ad hoc. Yeah, but so it is. But it's the same ad hoc. Okay, we're not introducing a different ad hoc. Yes?
So in that model, is the previous universe just entirely empty, just with the scalar field?
So the scalar field will have a certain epsilon. The matter and radiation, there may exist matter and radiation also in that period. So when I should say it's dominated by a scalar field as we come close to the end of the contraction. If we go far enough back, and if its epsilon is large compared to matter and radiation, it will become a subdominant component. So if we take Devin's case and go all the way back to the beginning, there'd be hardly any scalar field energy at all. The field would be more or less at rest, with almost no energy density. You'd have a thin veneer of some matter and radiation. As you contract, you'd go through different phases where one form of energy after another dominates. But as you get closer and closer to the contraction, the field, the degree of freedom with the largest epsilon is going to come to dominate. So I like to call it survival of the largest. If you wait long enough in your contraction, it's going to be the one that's going to come to dominate is going to be the one with the largest value of epsilon, which we're going to choose to be our scalar field. Okay? Just like in inflation, the idea is to rig something where there's some form of energy density which is a very small epsilon close to zero. In this case, you put it as an initial condition that it has to dominate. It doesn't occur that way naturally. You have to put it in by hand. Yeah?
At the most contracted region is the idea that we don't get into any quantum mechanically dominated era.
Don't jump ahead. We'll talk about it. There are different ideas that people have when they think about these models. They essentially break into A, which you said, you bounce before quantum gravity and other big quantum effects become important, or B, I'll assume we go through such a phase and that helps us through the bounce, and quantum gravity helps us through the bounce. So there are two different ideas, two sets of ideas that people, different groups play with when they think about these models.
So if you do assume that quantum gravity helps you through the bounce, like is this first bullet here still like a concern?
Which part?
The fact that like...
Oh, that's a reason. Yeah, you should be worried. Yeah. So I've given away that I'm not a big fan of that possibility. I think actually the lesson we've learned about the quantum runaway effect and multiverse is that we never want to be in the phase where quantum physics dominates over classical. You should be trying to construct models which are deterministically, classically dominated. You're going to quantum, I'm not saying there's quantum effects, there's quantum gravity, but they're never dominant. Then you have a theory which is deterministic and predictive. And since you're trying to explain very special properties of the universe, you'd like to explain why those are a natural outcome, not just one of an infinite number of outcomes, why they're the natural outcome of a deterministic, classically dominated theory. And we've never had a theory of that sort. By the end of this class, I will present you such a theory, an example of such a theory. But that's, but I think it's a target, an example of a target, for me, a pleasing model to think about. As opposed to one where you assume you go through some quantum dominated phase and somehow it sorts itself out. But we don't know. This is a subject of debate. You're allowed to think about different ideas, but you then have to think about how I go from quantum. So you not only have to go through this quantum dominated phase, you have to explain how you go from a quantum dominated phase to a classical dominated phase, how you don't lose track of whatever happened of this stuff, because you're going to use this period to help you smooth and flatten the universe. You don't want to lose that by having this quantum dominated phase. There's a lot of challenges if you go that route. Okay, whereas if you don't have to go that route, don't. Just don't do it. If it's trouble, don't do it. Okay, but that means we have some control parameter over here, where just like in inflation, you're allowed to choose your epsilon by choosing your potential. That's essentially what you're doing. You do have a degree of freedom here, which is, depending upon the potential for your scalar field, you can produce different possible values of epsilon. Okay? Okay, so there's something that you've looked at in homework, but we haven't discussed yet in class, which shows up at this point, which we can't ignore, which is the anisotropy. So, really, if you assume some random beginning, we'll keep the homogeneity for the moment, just for the sake of, just to keep some simplicity in the discussion. You don't not only have to worry about the spatial curvature, but there's another term, which you derive from homework in a homogeneous anisotropic universe, which is the anisotropy term. That's a term which we did, yes?
Maybe you mentioned this, but when we did this in the homework, we got rid of K for some
Yes, I think how you work out the spatial curvature term. So in general, we're going to have some spatial curvature term, which I'm being a little bit sloppy about. It's going to be some spatial curvature term that depends upon 1 upon a squared. It's going to be more complicated than this, as I'll just describe in a moment. But you would have guessed if I just wrote it down alongside the other term, it goes 1 upon a squared. And then you'll have this one. Okay, let's just, if you want to, for my purpose of my argument, let's just think of this, just forget it for the moment. We'll come back to it in just a moment. Okay? Now, in the expanding universe, this is not a problem, because 1 upon 8 to the 6 decreases faster than any other component. It is true, as you go back towards the Big Bang, What it does tell you, as you go back towards the Big Bang, you do expect this term to dominate. So among the things we didn't consider about inflationary initial conditions, it wasn't just the gradients and the field